279 meters, 59 stories. 4 stilts, each 9 stories tall, placed at the midpoints of every side, not the corners. A 400-ton damper at the crown. This is the Citigroup Center, and for one summer in 1978, it stood minutes from collapse. The story begins in Midtown Manhattan, on a city block at Lexington and 53rd. A small Lutheran church anchors one corner, refusing to sell unless its new sanctuary can stand untouched on the same ground. The challenge passes to architect Hugh Stubbins and structural engineer William Lemessurier. Their solution will be unprecedented. To leave the church corner entirely free, the tower will not rest on conventional perimeter columns. Instead, 4 enormous stilts at the midpoints of each face will lift the whole building 9 stories into the air. Below them, the church will be rebuilt as a separate volume. Surveyors mark the lines. Site preparation begins. The original block is cleared in stages. The old church is dismantled stone by stone, photographed and cataloged for the archive. Adjacent brownstones come down next, their facades cut away from neighboring buildings with care. What remains is a deep rectangular wound in the Manhattan grid, lined with sheet pile walls braced against the surrounding bedrock. Excavators bite into the schist below street level, lowering the floor of the future basement more than 15 meters. Dump trucks queue along Lexington Avenue, hauling spoil out through narrow city traffic. Deutering pumps run continuously. Engineers monitor the adjacent subway box and the sewer lines feeding the East River. Every cubic meter removed must be accounted for, every adjacent foundation watched for settlement. The pit deepens slowly. At its center, 4 enormous concrete footings will soon receive the loads of the tower above, each footing carrying roughly a quarter of a skyscraper. Reinforcement begins at the base of the pit. Steel cages the size of small houses are assembled on the surface, then lowered into position by mobile cranes parked along the curb. Each of the 4 footings is poured in a single continuous operation, with concrete trucks lining up through the night. The mix is specified for high early strength. The column loads above will be among the most concentrated of any tower in the city. Anchor bolts protrude from the cured surface, waiting for the column base plates. Below the slab, foundation walls climb to street level, forming the basement that will hold mechanical systems, parking, and the new sanctuary's footprint. By the time the perimeter slab is poured, the geometry of the building is already visible in plan. 4 points of contact, evenly spaced along the sides, leaving every corner of the block open to the sky. Steel arrives by truck from mills in Pennsylvania. The first members lifted into place are the great columns themselves, built up from welded plate, each one wider than a city sedan. Mobile cranes raise them in sections, splicing them as they climb. The columns rise 9 stories before any floor reaches across between them. From the sidewalk, the effect is unmistakable. The building has no corners on the ground. Pedestrians can walk diagonally beneath the plinth and look straight up at exposed steel. Above each stilt, the column will eventually meet a network of diagonal braces that carry the entire load of the tower inward to these 4 points. The geometry is elegant on paper and visible from blocks away, but every kilonewton that the floors above will collect must funnel through this narrow throat. The tolerance for error in the bracing system when it comes will be vanishingly small. With the stilts in place, the structural frame above begins to take its distinctive form. Tier by tier, the floors are framed in steel, and the diagonal braces are installed in chevron patterns across each face. These braces are the secret of the design. They collect the wind load from the entire tower and channel it diagonally down to the 4 central columns below. Without them, the building cannot stand. Inside the perimeter, fabricators bolt the brace gussets to the column flanges. The original specification calls for full penetration welds at every critical joint. Cost estimates and schedule pressure will eventually push the contractor to substitute high-strength bolts at many of these connections. A change approved by the engineering office in good faith, based on simplified load assumptions. No one at the time recognizes how sensitive the structure will be to wind, striking the building diagonally across its corners. The frame rises floor by floor. Steel deck is laid across the joists and topped with light concrete. Curtain wall units, finished in aluminum and silver gray glass, are hoisted from the street and clipped into place behind the structural skin. From a few blocks away, the tower's silhouette begins to emerge above its neighbors, a clean prism with no visible base, perched on those four central legs. Inside, mechanical floors are roughed in. Elevators are installed in the central core. The pace of work is steady but cautious. The engineering team revises load checks as the upper floors are added, monitoring the deflection of the chevrons under their own weight. The corners of the building are now visibly cantilevered out from the central columns, a constant reminder of the structural choice that defines the project. Pedestrians stop on the sidewalk and stare at a tower that seems to ignore them entirely. Near the top of the tower, on the 59th floor, a room is set aside for one of the most ambitious experiments in the history of skyscraper engineering. A 400-ton block of concrete is installed on a thin film of oil, free to slide horizontally within a frame of springs and hydraulic actuators. This is a tuned mass damper, calibrated to the natural sway period of the building. When the tower leans in one direction under wind, the block resists, slides the other way, and absorbs the motion. It is one of the first installations of its kind in any high-rise. The system requires uninterrupted electrical power to function, fed by dedicated circuits and a backup generator. In normal conditions, it reduces the perceived sway of the upper floors by roughly half. In severe conditions, it will become more than a comfort device. It will become a safety device. Above the damper room, the tower closes with its most recognizable feature, a roof sloped at 45 degrees, originally conceived to hold solar collectors. The collectors are never installed, but the sloped crown remains, giving the building a profile that reads instantly against the Manhattan skyline. Crews fix the last steel members and pour the topmost slabs. From street level, the tower now stands at its full height of 279 meters, balanced cleanly on its four central stilts. The interiors are fitted out floor by floor. Conference rooms, trading floors, and offices replace the bare deck. In 1977, the building opens for occupancy. Citigroup moves in. Tour groups gather on the plaza to look up at the small new sanctuary at one corner and at the impossible tower above it. To the public, the project is finished and triumphant. To its engineer, it is not. In the summer of 1978, a question reaches William Lemessurier's office. An engineering student, studying the building for a class project, has noticed that the chevron braces carry diagonal wind loads directly into the corner columns above, and the corner columns now sit at the midpoints of the sides, not the corners. Lemessurier reruns the calculations with quartering winds, the kind that strike the building at 45 degrees. He learns in the same week that many of the brace joints were built with bolts instead of welds. The combined effect is catastrophic. In a 16-year storm, the joints can fail. The tower can fall sideways into Midtown Manhattan. Crews are quietly assembled. Welders work at night while the building remains occupied, plating over every critical joint with steel and full penetration welds. A hurricane evacuation plan is filed with the city. A newspaper strike, by coincidence, keeps the story off the front pages. By autumn, the welding is finished. Every chevron joint has been reinforced. The tuned mass damper, originally installed for comfort, is now part of the safety case during the repair period. No storm of the magnitude feared ever arrives. The building stands. The full story is not made public for almost 2 decades. When it is, it becomes one of the most studied cases in structural engineering. A reminder that small substitutions in construction can interact with rare loads in catastrophic ways, and that the responsibility of an engineer does not end at the topping out ceremony. Today, the Citigroup Center remains in service on its 4 central stilts, the church still standing untouched at its corner. The tower carries its load quietly. The lesson it taught the profession is heavier than its steel. The difference between a building and a disaster can come down to a single conversation and the willingness to have